This is an example of bundle arcuate fasciculus left in native space and FA projected on the bundle. Here we can see the legend where green color means fractional anisotropy near 0 and red means almost 1. Here we can see how the fractional anisotropy varies across the length of the tract. We can see in the middle it's more around 0.5, and at this location it becomes more around 0.9, and at the ends is very low. So analyzing this whole bundle as it is will be difficult, or maybe it doesn't even make sense, because as we look at this bundle, it also has a different shape as it starts and ends. At the end, there's a lot of fanning, and in the middle, it is more consistent and it has a same shape here. So it makes more sense to look at specific locations of the bundle and just analyze those specific locations where the shape is similar and also the fractional anisotropy or any other DTI measures is consistent, so that we don't have too much variance in our input data. To deal with this problem, we have created bundle assignment maps in BUAN, where we start with A given the input bundle and having a model bundle centroid. So we create this model bundle centroid that you can see with different multiple colors here, which is generated from the model bundle that comes from the atlas. And this green bundle here, it is the extracted bundle from auto-calibrated Rokem bundles, and this is in common space. So these both centroid and bundle are in the MNI space here. In this example, this centroid, which is a streamline, it has 100 points, and each point is visualized with a random different color. What we do is we calculate distance from each point on every streamline with all the centroid points here. So if this point that starts from here, it will be close to some centroid. Maybe if this is the first centroid, it will be near the first centroid. And then we calculate distance between all the points on all the streamlines with all the centroids. So wherever the distance is minimum, we give it the label that this point belongs to this centroid number. So the number of the centroid becomes the label for that point, that which centroid it belongs to. Here is a visualization showing that how we create these segments. So this bundle is now segmented into 100 segments because we had 100 points on the centroid streamline. So this is the location of all the points that belong to this segment, to that centroid. Now it makes sense to look at those specific segments because those are similar in shape, and as we saw earlier, it will have similar values of DTI measures there. Let's see a better example on the simulated streamline data of how bundle assignments are created. Here we can see this is the input data where we have 7 streamlines and length along the track or streamline. In this case, we have just kept the length from 1, 2, 3, 4, 5, and then on the y-axis we have FA values projected. In the middle we can see we have visualized here a model centroid in yellow with the points as red. So in this case the centroid has 5 points. So we will calculate the distance from, let's say, streamline 1 and its point 1 with distance from this point with all the 5 points on the centroid streamline. And then since it's closer to this one, we will assign it segment number 1. Then move to the next point, whichever centroid it is closest to, we will assign it label that it belongs to that centroid. So centroid number 2, and so on. Here in the right we can see how those segments are created. So we are not reordering data or resampling data or doing anything at all. We just keep the data as it is. We just give it extra label. You can think of it as this is a soft assignment where we just give it a label to it. And here is the visualization of how it works. So all the points that are near centroid 1, they'll belong to this one segment. Here we have just given those, I've just created those lines to show the segments. So here the interesting part is here. If you look at the streamline number 5, this is the first point, but it doesn't belong to the first segment. It belongs to second segment because this is more closer to the second centroid, which makes sense because the streamlines come in all shapes and sizes. So this starts later as compared to the other streamlines. So we keep it in the second segment and we don't assign it to the first segment. And also here, if we look at the streamline number 7, the last point, it belongs to segment 4 and not 5, and so on. Here is an example of CST bundle where we have visualized the centroid in yellow, and this is the bundle. And here we have divided it into 40 segments, and we can see how it looks like. So we save this information about these created segments and the DTI measures projected on it, for example, FA or MD. And then we give this data where we have data coming from two groups. In the red we have from patient data, and in the green we have control data. So this shows the bundle profiles with the bundle segmented into 100 segments and then the DTI measures projected on it. Then we input this data to statistical model to find group differences along the length of the tract. Here we are using linear mixed models to find group differences. In linear mixed models, what we are doing is we run one linear mixed model per segment. So 100 segments, 100 times different linear mixed model is run per segment. One more thing I want to mention here is, so this centroid is same when we are creating these bundle profiles for all the subjects. So we know that all the subjects from subject 1, 2, 3, all the points that belong to segment 1 will be near this centroid. So they will belong to the same location. They will correspond to the same location. And when we project the anatomical measures such as fractional anisotropy, we go back into the native space to measure those. We do not do any registration here. So how we do that is, how we are able to accomplish that step is because we have this soft assignment information that this point belongs to this segment. So when we go back to the native space, we just get the data, all the points that belong to that segment. And then we are able to run linear mixed models. Here we can see the plots for arcuate fasciculus, FA, CSA, GFA, MD, and AD. And here we have p-values, minus log of p-values. We can see this area where there's a significant difference between two groups, where the p-value is less than 0.001. And finally, we explicitly highlight that area in BUAN where we see the differences between two groups. Now there could be different areas for different measures. For example, in this example, here the red area highlighted shows that there are differences between two groups in MD and AD. And yellow area shows differences in FA and GFA. And we get this information from linear mixed models. I'll just give a brief review of how we are using linear mixed models. In the next session, you will hear about linear mixed models in detail from Dr. Harris. So this is the formula for linear mixed models, and in our case, the fixed effect term is accounted for the population mean, and the random effects coefficients account for the subject-specific deviation from population mean. This random effects model are used to properly account for the correlations between points on the same streamline belonging to the one segment for a specific subject. The response variable will be the anatomical measures such as FA, MD, RD. The experimental data that we used for BUAN came from the Parkinson's Progression Markers Initiative PPMI dataset. We selected a specific age group from 39 to 61, and each group, patient group and control group, had 32 subjects, 14 female and 18 male. We kept the same ratio of male to female in both groups and also the age ratio so that we don't have any bias because of different age groups or different ratio of male to female. Here are the results on fractional anisotropy, where in these plots we have left and right hemisphere tracts, and most of these. In some we have just one, like in the first row here, third column CC mid, or in the last we have V. Let's zoom in and look at some of these plots. So here I have zoomed in and we are looking at few of the plots. Here we can see FOF left and FOF right. On the x-axis we have the segment number, and on the y-axis we have minus log of p-values. And in this area where we have these horizontal lines, if something comes under these two lines, we say there is a high significant difference between two groups because the p-value is less than 0.001. And we can see here in FOF, both left and right, there is some difference around 60 segment. And for example, in ILF, we see something around from 70 to 80, and so on. Now these were in this way we found exact location where there were the group differences. But what are the group differences? So to see what exactly is the group difference, is FA increasing or is FA decreasing? So here we have visualized the mean group FA and for an MD in the bottom row for two groups, where red shows patient and green shows control. So let's zoom in to some of the plots here. So here we can see we have arcuate fasciculus, CST, FOF. In the case of FA, we see wherever we have the higher group differences, for example, for AF, we see around 70. And if we look at what are the group differences, we see that the patient has higher FA value as compared to the controls. And we find similar trends for CST as well. Around 70, we see that FA for patient is higher. And also in the FOF, we see around 60, actually. Here it was around 70, higher value of FA in patients as compared to controls. And if we look at the MD, since MD has very small values, so if there is just one outlier, we will have a spike in the mean, as we can see here. In the case of CST, around 10th segment, we see there is a spike, which happens to be because of there was one or two outliers that had higher value of MD here. But if you look closely, linear mixed models is not giving it any higher significant p-value. We don't say that this area or this comes under the significant group difference. This kind of proves that linear mixed models is working well and it could deal with outliers. And again, if we see here in the FOF around 90, there's a spike, but p-value is not significant. And another trend, if we look at here, is in this case it's very small, but actually MD is lower in patients as compared to controls. So we find group differences in different DDI measures and exactly what the differences are. We can also visualize those with BUAN. Here is the final overview or summary of bundle profile creation and the statistical analysis on those bundle profiles. So first we create these segments. Here we are showing FOF left on the top and FOF right in the bottom. And we have created 100 segments for both bundles. And then we have this data for 64 subjects in this experiment of PPMI data, where 32 control and 32 patient data had the bundle profile created in this way. And then we take data from, for example, the first segment here, from all of the bundles, FOF left bundle from all of the subjects, and we give it to the linear mixed models, and then we move to next segment and so on. So we give it to 100 linear mixed models, and then we get the outputs here as shown here. We are showing for 4 DDI measures, FA, RD, and then we also have CSA, GFA, generalized fractional anisotropy, and CSA QA. And in this we see for the left FOF, we see around 60. There are some group differences for FA and also for MD and also for GFA and QA. And in case of right FOF, we have kind of similar trend, but maybe not so much for RD and QA. And then from this information where we have that the significant group differences where the p-value is less than 0.001, we are able to locate especially exactly where on the bundle are those segments. So in this case, those were here, 58 and 62, and we can visualize exactly which location it is because we already know the information about the segment number. And also in the right FOF. This is great. Now we know exactly where there are the group differences, but let's see what are the group differences. So here in the details, we are showing the histogram plot of count, where on the x-axis we have the FA value in this plot, and on the y-axis we have the count for how many subjects had this mean FA value for that segment. So this is for this region, 58 to 62 region. We show what are the FA values, mean FA values per subject. So here again, the same convention where red is for patient and green is for control. So if we look at this at FA, in FA increases, like the FA value, mean FA value increases for patients as compared to controls. And for RD, actually it decreases as compared to control. And in GFA, it increases in patients, and again in QA. This makes sense because this is fractional anisotropy and generalized fractional anisotropy. They should have similar trend. And we again observe the same trend for FOF right. So I'll stop here, and in the next part I'll talk about bundle shape similarity.